Question 2 is simply an application of Fleming's left-hand rule. If you use the correct directions, which is pointing to south, and then the current flow is in this direction, you should get the correct answer, which is B, vertically upwards. If you've got A, you are probably pointing in the wrong direction here with the current. The correct answer to the next question is D. This is a really interesting question. It's asking you to think about the direction of the field lines. So we're considering point P, and what is the resultant force acting at P? So if we draw the field lines around each of these, we'll see this field line arrangement. I've left the last field line because it will be a little bit of a mess, but basically all of these would coincide at P. So what we're going to do is we're going to look at the direction of each of the forces acting at P thanks to these 4 field lines. Now if you use the right hand rule, the corkscrew rule, it will give you the directions, which I'm going to add now. Okay, so you can see all the field lines acting there. What I'm going to do is I'm going to show you the direction for each one. This one here has a resultant force this way, acting at P, in that direction. This one here has a force acting this way. This current here has a force acting again in this direction, and this one here has a force acting in this direction. So what you have, if I draw it on the side slightly neater, is you have 2 forces acting this way at P and 2 forces acting this way at P. So the resultant forces, well, if you add 2 forces like that together, the resultant would be nose to tail, and as you can see, it would be this way. That is a tricky question, and I wouldn't recommend spending too long on a question like this in the real exam. This is a question about the F equals Bill sine theta formula. Okay, so firstly, force per unit length is equal to P. So that is then equivalent to B, the magnetic field strength, current, sine of the angle, which is basically getting rid of the L. And now we need the equation in terms of magnetic field strength. So in terms of B equals P over current and sine of the angle. Now just to double check that the angle that they've given us is actually the one we're supposed to be using, if we find the sine of this angle, will we be looking at current perpendicular to field lines? So just check, sine of this triangle would give us this length here, okay, which is indeed 90 degrees to the field line. So yes, it is okay to use sine. So the answer would be C. Okay, so this is about the electric motor. And though it's very easy to make one, well, relatively easy, for most of you anyway, it's not so easy to answer questions on it. So it's important to go through this question carefully. Okay, we have the simple DC motor. So it's exactly like the one that you made. We've got a single rectangular coil, which is here. It's the rectangular coil, rotating between the poles of a permanent magnet. And they have not shown the connections between the coil and the battery. And we have something called the split ring. Now the split ring is here, and it's basically a way of disconnecting the whole coil. So you can see there is no connection between there and there. And it's pretty much like the one you made. So what is it asking? On the diagram below, draw connections from the battery B to the split ring so it will rotate continuously in one direction. Now, there is a bit of a trick to this, and luckily you've made it. So what you should have added is a connection up here that ended, okay, in some kind of L shape or something like that, okay, or made it very, very similar to what you actually made. You had two wires sticking up like that, and then you had the coil moving in the center, okay. So anything like that would be okay. And this would not be okay. Okay, it's really important that you show that there's not a direct connection here at the split ring. The second part, most of you did okay on, but you've got to be very, very careful with reading the question. It says, on the diagram above, draw arrows to show the direction of the forces. It's not asking for the direction of the movement. So it's very important that you use an arrow to point down and an arrow here to point up, because that's the way the force is acting. What is not appropriate is for you to draw the direction of the motion, which is clockwise or anti-clockwise in this case. Okay, this shows you the direction of motion. It does not show you the direction that the force is acting on. Also, how did we get this force? Well, the best way to do it is to concentrate on one side of the armature, this wire. Considering that this is the positive terminal, we follow the conventional current around. So the conventional current goes around here and then comes through here and then follows through that coil. So you now have a direction of the current in that way, and you have the field in this way. And if you use your left hand rule, you should find that it moves downwards. Okay, so two really neatly drawn arrows on the armature in the correct direction should have got you the 2 marks, or the mark, sorry. Now the third part is actually very tricky, because even if you do understand how this works, it's very important that you say exactly the right thing. Now the mark scheme allows you to explain what would happen if you didn't have these 2 wires sticking up, or brushes as they're called. So what you could have said was that the connections, as referred to in the question, are such that if the wire was connected to the coil and not disconnected, then the force would always be in the same direction, even when it went round 180 degrees to here. So what would happen is, because you have a coil, the wire would experience a force because the current's going this way, and as it turned and flipped over to the other side, so as it turned, went round and flipped over to here, then you would see, you would experience once again a force down, because the current here would be in that direction. So therefore the movement would be not circular, but would be backwards and forwards. When it's on this side, let's draw it a kind of side view. When it's on this side, the current flow is into the paper, and so it experiences a force down. It spins round to here, and if the current is still flowing into the paper, as a cross I suppose, then it would feel a force down again. So what you have to do is you have to use the brushes, or these wires that disconnect should reconnect with the other side of the armature. Okay, so when the split ring is in contact with the brushes, then the direction of the force is always the same. Okay, even 180 degrees later. in order to move as a circle, there must be the wires, or brushes, should call them, need to disconnect and connect, and reconnect with the other side. Okay, here all you have to do is look at the field lines. Now you know that the field strength, B, is represented by the field line density. If the lines are close together, they're strong. If they're far apart, they're weak. If their distance stays the same, then they are constant. Now the question asks, state whether the field strength at A or B is constant, increasing or decreasing when measured in the direction from A towards B. So as A moves towards B, so imagine, I know the wording is a little bit strange, but imagine a particle here, okay, is moving in this direction towards B. What is it experiencing at A? At A, it's experiencing field lines that are not changing. So there you would have constant. Okay, as that particle moves further into this direction, what's happening as it goes through B? Well, as it goes through B, it's experiencing field lines which are getting further apart. So the density of the field lines is becoming less, and that means that it is decreasing in field strength. The next question is a bit sneaky, although one or two of you did get it correct. It's saying, why can field lines never cross or touch? Well, imagine an iron filing who's just lying there. What would happen if it was in field lines at the same time? What happens when two field lines act on it? Well, when that happens, you have an object experiencing two forces. And although this might happen, or in fact this does happen, when you get two field line patterns interacting each other, like for example north and north, south and south, you've seen what happens when the field lines overlap. You end up having a cancellation of forces. Okay, but when you just have one magnetic field, you only have one set of field lines, and the objects that are influenced by it only ever experience one force. So the correct answer is because then the object that experiences the force would be pulled in two different directions, and this doesn't happen. Okay, this last question was actually way more straightforward than some of you thought. Okay, so remember what we've done so far. We've got field lines due to a magnetic field, which when interacting with a charged particle, be it an electron or a positive particle, will exert a resultant force. Now, what's really important about that force, and what pretty much defines the movement, be it circular or elliptical or whatever, is the following statement. When a charged particle experiences a force, that force is at 90 degrees. And because it's 90 degrees, and because this particle is free to move, then what you get is a resultant circular path. Okay, and to give a bit of follow-up, is why is it circular? Because there's always a 90 degree, always 90 degrees, always, towards the center of a circle. So State and explain whether the field of force is electric or magnetic. Well, you have to say because the field lines, because the path is circular, it must be experiencing a force at 90 degrees. That only happens with magnetic fields. Okay, just to recap, this is something we'll revise a little bit later on, but if you really consider electric fields like, for example, positive and negative plates, what they do to little charged particles is they make them move up or down. Okay, don't make them move in a circle. So the magic word here is force at 90 degrees relating to circular path. Next part, the path of each of the two particles is spiral. Okay, one particle is spiraling clockwise, the other is anti-clockwise. Now, if you consider the left-hand rule, the thumb is the one that tells you which direction it's moving in. Okay, so you need to think what arrangement would mean that for one of the particles, the thumb points up and one of the particles moves down. Why would there be a difference? Now, it can't be the magnetic field because that's not changing. So it must be the charge. In fact, the correct answer is that they have different charges. One is positive and one is negative. The next question requires you to do a lot for 3 marks, but again, this question does come up a lot, so it's worth looking into. Outline why each path is a spiral rather than a circle. Now, a perfect situation would be a circular path. Okay, and just like with many, many areas in physics, there is always going to be some kind of energy loss. Why? Because these are charged particles. They interact with the particles in the surrounding area and they lose energy. So because they're losing energy, and this is why we need to think about our formula. If we relate the formula to this answer, then we'll get full credit. So if this particle loses energy, what happens is its velocity decreases. Because its velocity decreases, and because the radius is proportional to the velocity, then the radius will decrease as well. And because the radius of the circle is decreasing, we're getting a spiral. Okay, so it is a bit complex, but it is a very common question. So always revise this idea of radius being proportional to mass, proportional to speed, and inversely proportional to the field strength and the charge.